let's take a look at where we are. Let's take a look at the few new concepts for Lyapunov stability analysis in modern control engineering. By now, we know how quadratic function for general state space systems, how these two can be connected. We went from a simple concept of energy-like functions, such as kinetic energy plus potential energy. We recognize that these are actually can be more compactly written in this matrix notation using advanced linear algebra, actually simple linear algebra. And we looked at also specific properties of matrices, square matrices, that will become continuously relevant. We were saying that a matrix P or P, if we just write a simple form like this is only saying that this matrix is a square matrix. Its dimension must match, the row dimension, column dimension must match in order for this quadratic form to apply. And we started narrowing down to more advanced properties of matrices, square matrices. We said square matrices that have these property, P transpose equal to P, belongs to the symmetric matrices. And once a matrix becomes in a symmetric form, we have these advanced properties. First of all, we know that all eigenvalues, all lambdas, are real. So there won't be any complex eigenvalues that's going to become appearing here. What's more, because eigenvalues are real, we can actually order them. So real numbers, there are only three cases. Real numbers can be positive, negative, or zero. So we can order these eigenvalues according to the size and the magnitude. And the important property of the symmetric matrices is actually the eigenvalues are bounded. So these eigenvalues, they will be bounded, all of them will be bounded by a maximum value and a minimum value. And then the maximum value is actually the maximum possible value of this. So take any vector x, do this multiplication. The top part obviously is a scalar. It's x transpose, it's a row vector. If x is a column vector, this is a row vector. Row vector times the matrix times a column vector, this is a scalar. This is a magnitude of this vector over here. Try all the possible x. The maximum of this product will be the maximum of the eigenvalue over here. And same thing, for the minimum, you just replace max with minimum. And because we can order them, these eigenvalues now give a immediately very powerful property. It's the symmetric eigenvalue decomposition theorem, which is saying the concept. We can, for general matrix, if P is only square, we can say potential, we can have a potential diagonalization. Which is saying this P, if it's just a square, meaning that we can do potentially P equal to T inverse capital lambda T. This is a three matrix product. It's cumbersome to compute. Doing an inverse is tedious for most of the cases. If it's symmetric, then actually this will simplify to, you can decompose P in a form that's amazingly simple. So I equal to 1 to n. If it has n eigenvalues, then do this addition of lambda I, and then let's do the eigenvector to be I will use V transpose. So if P is symmetric, you don't have to do this. You can directly have this advantageous decomposition of P. Question?
Sorry, you mean the
Eigenvector associated to the eigenvalue lambda. So you can do this. This is decomposing it into small chunks of outer product of the eigenvectors, and then multiplied with the eigenvalue. This form, now, you may still think this is a little bit not obvious, but now, let's go back one step. Take a look at this. This we said is the energy-like function. It's the addition of multiple square quadratic terms. Now, if P can be decomposed into this, what will happen to this form, quadratic function here? This one is going to become, if symmetric, is going to become half of X transpose. This P is lambda I, and then I from 1 to n x. So by symmetric eigenvalue decomposition, this general quadratic function becomes this, which is, I can take out the scalar 1/2 in the front, and the inside, you can multiply this to the inside, multiply this to the inside. It becomes sum of lambda I x vi, X transpose vi. This is the first part. This is a scalar. It's a column vector transpose times the column vector, so it's a scalar. And then for this part over here, you get vi transpose times x as well. This is also a scalar. And if it's a scalar, it doesn't matter how you multiply it out. So you can write it as x as this one, or you can write it as this one is the same as x transpose vi. If this is a scalar, then it doesn't matter the direction of the vector you multiply. Or in other words, this is actually, you are doing the transpose of a scalar is itself. So you can write this one in this form as well. In other words, inside, you actually get this. So now, isn't this almost in the same form as this? We said this one, if P is just a general square matrix, then it's not that advantageous. For us, if it's a symmetric matrix, then we see this form really is indeed nothing but something like this. It's just written in a more compact form. It's a submission of small quadratic parts. Each of them is about x. That is the true connection now between symmetric matrices and this energy-like function. Yeah, just as a side note. So your classmate is saying that, hey, we looked at, we said if x is a state, then usually it will have oscillation behaviors inside if it's a dynamic system. That oscillation behavior is coming from the eigenvalues of A. Here, this is not the A matrix. This is a form that is used to construct the energy-like functions. So that's why it's different. All right, now you see symmetric matrices are great. What is one little thing that is still potentially bothersome? We were saying that symmetric matrices, the eigenvalues are real, so they can be positive, they can be real, they can be negative too. For a energy-like function, ideally, what's the best scenario? The signs has to be always positive, all of them. But this is not guaranteed just yet. Some of these eigenvalues, they can be negative right now. So what we will go through today is completing the picture and going from symmetric matrices to positive definite matrices. And it turns out if it's positive definite, then it is truly very much like energy-like function. We know that the energy is going to be guaranteed to be positive. More formally, positive definite matrices are connected to symmetric matrices, and then positive definite functions are related to the positive definite matrices. This is just saying the matrix itself. This is a function. This function consists of matrix inside. So same story here. Positive definite functions will contain the positive definite matrix inside, as well as some state vectors. And then after we clear this, this positive definite function is going to become a candidate of a Lyapunov function. And then we use the Lyapunov function to judge the stability of a dynamic system.